Yeah, there was a problem with the internet connection. Sometimes my router dies on heavy upload, which is due to some bug in the Linux kernel driver of its network chip. There's a workaround, which I forgot to enable, but now it's enabled and the connection should be stable again. Good. Okay, so that's nice. Okay, so I want to get started with RISC-V on Managarm. We have some very simple support code. So basically we have a RISC-V entry stub that does nothing. It just loops around forever and does no real work. And now what we actually need to do is we need to implement the same code that other architectures implement. So that's what I have open here. So basically we need some driver for printing. That shouldn't be too hard. And then we need to implement some main function. And the main function is actually generic in a way. Right now, each architecture has its own main function, which is kind of annoying, and I want to get rid of that. Yeah. By the way, this is all in the pre-kernel still. So Managarm loads its kernel in 2 stages. It first loads a pre-kernel, and then it loads the real kernel. And the reason for that is that the pre-kernel can set up memory and stuff like that without complications. Basically, it can set up memory without being virtually mapped itself and so on. So it runs in non-paged mode, does not use any interrupts at all. It does only really simple stuff. It basically discovers the memory ranges that exist, arranges them in some nice data structure and passes them to the kernel. Also loads the kernel as an ELF file, which means that the kernel is always compiled to the same format, regardless of the architecture. Yeah, and that's what we need to change first. So this pre-kernel is what we need to change first. This is the ARM pre-kernel for Camus virtual architecture. So basically what we do here is we pass some device tree for the memory ranges. So the device tree is just some generic description of the machine. Yeah. Then what happens here? We mark some regions as reserved. We find the init RAM disk in memory. Okay, then we call here into generic code to set up the memory regions. So yeah, to basically decide which of the memory regions are usable and which aren't. For example, we discard really small ones where the overhead of managing them would be higher than the benefit. Yeah. Then we set up paging without actually entering the paged mode yet. And finally, we construct some data structure that we pass to the kernel here. And that's basically the code that we also have to code for RISC-V. And because most of it is actually not that architecture specific, I want to move that to a general file that all architectures can use. But first of all, we need to get started by implementing some driver to print stuff to the to the serial log. Otherwise, yeah, it will be a pain to debug everything. Okay. Yeah. Okay. Yeah, I guess one thing that we want is having a stack, which we don't have yet, but that should be easy to add. Yeah. And we can also by the way, it's also a good idea to just copy from the toy OS that we developed earlier. Less of it, yeah, the chance to mess something up is lower if you just look up how it's done. Obviously. Okay, okay, we should be creating the stack in the BSS section, of course, and there's this base directive that we can use. Okay. And we allocate, I don't know. Okay, it's stored in the binary, so you shouldn't overdo it. Let's just go with 16K. Okay, these should probably be global symbols. Okay, that's actually not important because I guess we only set up the stack here. So we load the address of the stack into the stack register, right? Here, sp stack top. Stack grows from top to bottom, just like on x86 and basically all other architectures that Managarm supports until now. And now we want to jump to some main function, which should of course be global and external. I think we don't need to declare external functions, but I'm not entirely sure. Yeah, so let's jump to some function like that. Good. Okay, and now I want to create some generic file yeah, for the main function. So maybe let's go up in the directory hierarchy. I think there's already a generic main file, but it doesn't actually contain the main function. So let's create another one. And let's see how to integrate that into the build system. So for now, I only want to make the RISC-V port use the generic main function. Because I don't want to rewrite all other ports now on stream, and we probably want to do that iteratively because it's a lot of work. So yeah, let's not do it in a single go. But let's create this main function CPP, and then the RISC-V port just adds this generic main to its sources. Yeah. Now let's, oops. Let's jump to a window that I did not expect to jump into, in a different screen. Okay. Now let's try to rebuild the kernel. Okay, that failed because we don't have this function yet, but okay, we can simply add it. How did we call that? Main function. Okay. Okay, that worked, and now yeah, I have to export a different camo version for that to work. All right, so I assume that we are now in this main function because nothing else happened. Okay, but now what we need to do is we need to add code to print to the screen, or rather to this serial log here. This all the stuff above here is printed by the firmware, and that's expected and basically what we want to see. And now, now we also need to add some kind of printing code, which we add, of course, in the architecture-specific part. Okay, and we probably only want to add that for the virtual platform. Okay, so let's call it maybe early log, something like that. And let's take a look at the ARM code again to see how it is supposed to work. Okay, we need to define this function debug print character. Yeah. And it just prints a character, and it's in this namespace here, and I think it's defined in this arc HPP file. So we should probably just include that. Yeah. And here again, I guess we can copy from the ToyOS, which already has some function to print. Yeah, exactly. Basically, we're using this here to print. Yeah. Which is a firmware call. We're using the firmware to print stuff, which is fine at this point. We don't need any fancy driver. We can just use the firmware. Okay. So let's maybe just copy from there. What's this file called there? Okay, I guess I need this. Yeah, and let's change the naming convention to match what we have here already. Good. Okay, now if we look at the usage of this function, okay, it first takes an extension and a function that these are just two IDs that the firmware expects. So 10 apparently means print, and then a single argument, which is the character that we want to print. So to print debugging characters, we should just be able to do it like this. 10 C. Okay. Now let's see if that still compiles. Okay, it does, but I did not actually add it to the build system yet, which is of course a problem. Okay. So let's do that. Early block CPP should do it, hopefully. Or actually I can just add it here, right? It's a bit easier. Okay, it still worked. Okay, that's nice. Good. Now, if we take a look at the ARM code, let's do that. Then we can use this info logger now to print stuff. We should be able to do that. And this only uses generic code and then calls into this debug print character function. So we should be able to just call that now. Okay, and surely we need some header file for that to work, which is, I guess, the debug file here. Okay. And now we are getting some undefined symbols. We're getting an undefined reference to this info logger. Okay. Does the ARM file declare it? It doesn't. Is there any other file in the ARM code that does? Okay, we have this arc-cpp. Okay, some paging code, but it does not declare this info logger. There's some fault handling, which probably also does not declare that, right? No, it doesn't. What else is there? Nothing. And invert actually arc-arm-vert. Okay, so let's maybe just grab for it. Oh, it's in generic debug CPP. So we are not including generic debug CPP. Oh, I actually might have just disabled all the generic code to make RISC-V not complain about missing symbols. So I guess that's just the problem, that I basically disabled all the generic code. Okay, of course that's an issue. So let's not do that. So where does the generic code actually get compiled in? Okay, yeah, I think the reason is that in the ARM case we include this here generic sources, which we don't do in the RISC-V build system code, right? Yeah, okay, there's a to do for it. So let's do that. And the issue is that this will now complain about a different bunch of missing symbols, I guess. Yeah, because we have not defined the paging stuff yet. We need to define the paging functions for that to work. Oh, we're also missing a reference to this function. Why? I guess that's for the All-Winner platform. I guess the All-Winner platform is missing a reference. Yeah, basically this is the real hardware chip that we want to test with. Yeah. So the idea is to develop both for the virtual Camu platform and also for the All-Winner D1 platform at the same time, or nearly at the same time. It's probably a lot easier to debug on Word, so if stuff fails on Word, there's no real point in trying it out on real hardware. Yeah, but that means that we also have to add such an early log file to the All-Winner platform. Okay, let's do that. So let's copy the Word early log code to the All-Winner platform. And I think we do not really want to use the firmware to print on real hardware, because that might just not work. I think this firmware printing function is deprecated anyway, So it's not the best idea to use it, but I know that it works on Camu. So yeah. It probably also works on real hardware actually, because even on real hardware you get this OpenSBI log. You basically get this header too on real hardware, which means that the firmware is able to use the UART, which probably means that also the legacy function for printing works. Okay, anyway. For now should I just use the same code for now here? Okay, I guess that doesn't really hurt. Okay, we still get undefined references. Yeah, we did not modify the build system. Yeah, the build system for real hardware is a bit more complicated. We have to do some stuff with object copy to turn the ELF file into a flat binary. Then we have to turn the flat binary into a U-boot payload. And then we have to create some fast boot wrapper around it. And then we can actually boot this over USB on real hardware. And that actually already works. Yeah. So basically all this code here at the bottom of the make file for real hardware, well, only transforms the kernel image to a different format. Well, U-boot actually calls, or as far as I understand, U-boot runs on top of OpenSBI, does it? Okay, what might be possible is that U-boot basically reconfigures the URLs or so, and then OpenSBI can't use them in a meaningful way anymore. So basically, I'm answering the question in the chat by static. Or not question, but the remark that it might not work on U-boot, the firmware-based printing. Okay. That might be true. The Allwinner chip might run U-boot in M mode, but actually I think I saw the OpenSBI logo when I booted it. I won't boot it now because it's kind of annoying. I have to plug it into a USB port and so on. Yeah. First want to make Word work here, and then soonish, so probably in the next stream or so, I will make real hardware work. It shouldn't be a lot more difficult. Okay, we have to define these mapping functions. So let's first of all add to the RISC-V architecture some paging CPP. And let's copy from ARM the function prototypes. How was it called? It was called Arch-CPP. Okay, we want to copy the prototypes only. We want to copy this include. And okay, what do we need? We need map single 4K page. Basically, that is supposed to map a single page. Then, okay, there's a function get single 4K. I'm not sure if it's used or not. Maybe it's only for debugging. Okay, this init processor early function is also necessary, but probably should not go into paging CPP, but into some, I don't know, CPU CPP. Yeah, then there's a function to initialize paging in general. And I'm not sure what setup paging does. Okay, it's only called from another function. Also not sure why this function is getting past the kernel entry point. Okay, it calls into load kernel image. That's probably something that should be cleaned up. Yeah, this function looks a bit strange. I'm not entirely sure what the purpose is, but it's probably not named correctly. Okay, so let's leave these functions empty for now, because we first want to enter the generic, or want to make the generic main code work. Same goes for this function. Should probably follow our name or our coding style here and add these comments. And now we should also add that to the build system. So this does not depend on any SOC or any platform, so we just put it here. Yeah. And now let's see if everything compiles. For CPU, CPP does not exist. Oh, yeah, we have to use files here. Or rather, we have to put it into that clause. We have to do that because this variable ER sources is used in a different directory, so the relative paths just won't work. Okay, let's run. Okay, and the hello world from our generic main function works. Okay, that's nice. Okay, we get a bunch of unused parental warnings. You should probably silence these before continuing, because in contrast to the ToyOS, we also want to make sure that we get some reasonable commits, right? We don't want to have dirty code all over the place. That would be quite annoying to merge later on. So let's make sure that we do not cause any new warnings. Oops, compile. Okay, maybe we should also reconfigure to see that there are really no warnings. Yeah, seems to be the case now. Okay. Yeah. I guess we can already commit that. Because now, yeah. We have this generic main function. We did set up our stack so that we're actually in C code, and also printing works. So that's already a nice first step. So let's commit this subdirectory here, and let's check that we're not committing any stupid stuff. Okay, the paging functions obviously won't work because they're empty, but that's not a big deal. The logging stuff works, and I don't see a huge issue with that. Okay, the main function has a while one loop at the end, which is a bit ugly, but also fine. Yeah, so let's commit this. Yeah. This also adds a logging driver for API. Yeah. Hi, Cookie. Okay. Yeah, Cookie can later on rewrite the ARM code to also make use of the generic main function. No. Okay, what do I want to do next? Okay. Yeah. Okay, so next I want to somehow unify the main code. So if we look at the word code here, for example. Oh, the word code for ARM, actually. Okay, it does this device tree stuff, which is of course ARM specific. Actually, on RISC-V you also have to do that, so it's not only ARM specific, but some architectures use these device trees, others don't. But if the architectures use the device trees, then the code is somewhat generic. So I want to move that to some generic place. And then, okay, we have this paging code, and we have this code that sets up the information struct for the kernel. Yeah. And here we have some... Actually, what does this do? Lots of magic numbers. Okay, Cookie, do you know what this code does? It sets up some memory mapped I/O region for the ARM kernel, but I have no idea what this is, what address this is. That's the physical address that we're mapping here. Might be the UART. Is that used above? Yeah, it's the UART. Yeah, maps the UART so that the kernel can use it after enabling paging. Okay. Yeah, that probably deserves a comment. Yeah. Anyway, so this code here is somewhat generic. The device tree code is only works for some architectures. But the general flow is always the same. The general flow is basically discover which memory ranges exist. Yeah. Then find the kernel in memory. The kernel is already loaded because we assume that it's loaded using an init RAM disk. And then map the kernel using paging. And that's the general flow in all architectures. And yeah. And I guess what we want to do to make this work, basically to also work around the fact that some architectures use device trees, others use the BIOS or ICPI or well-known device maps or whatever. We will not make the generic code call into Arch-specific code. Instead, we will make the architecture-specific code register some callbacks, or basically register some steps that we need to run. And that's also something that we do in the main kernel. And I think it's a very successful approach there, so we're just going to clone it. Yeah. Basically, it's in this init graph file. It's in this init graph file. Now there's one issue, and that is we're using the main kernel's debugging functionality here. Yeah. Which is different and well, the code's in a different namespace than the prekernel here. So Thor is the main kernel, ER is the prekernel. which is a problem. We can't just include this file. And if we did, then it would just break due to these missing symbols and missing functions. I guess we somehow have to generalize this code to use an arbitrary logger. I guess what we do is we just pass to the constructor some, well, vtable, so some struct with a lot of virtual functions that basically get called whenever we want to log something or whenever we are in a specific part of the code or so. Yeah. So I guess I copy this file here out of the main kernel into some generic directory, which is, I guess, common here. Yeah. Okay, we have to get rid of this debugging stuff, but everything else here is generic, so that's nice. We also adjust the namespace. Wait. Okay. Okay, let's do that again. We remove the header file, we adjust the namespace here. Okay, the code is a bit yeah, hard to read because it makes use of a lot of template metaprogramming, but that shouldn't be an issue for now because we're only modifying where it logs stuff. Yeah, if this function realize node, yeah, let's first inspect where we log stuff. Okay, we log stuff in realize node, in realize edge. Then there's some logging here. Okay. So what we're going to do is we just... Wait, I'm confused. Ah, yeah, here. We just add some hooks struct or so, which just does and get some virtual functions. Virtual void on realize node on realize edge. And these should probably be purely virtual. And then these functions are called before and after this activate function, which actually does work. So let's call the other two hooks, let's call them pre-activate and post-activate. Okay, and then we're passing these hooks to the constructor of this engine, and we have to store it somewhere. Okay. Good. Yeah, I'll explain in a minute how that actually works. Or basically how this entire file works. And here I guess I'll just call hooks reactivate. Instead of logging, here I'll just call hooks.postActivate. Okay, there's a bit of logging here. There's a bit of logging here that I missed earlier. So let's also add that. Yeah, we forgot these arguments that, so basically we're making this code generic over the logging functionality. To make sure that we don't have to write the same code twice. Okay. And I guess here, for now, I will just delete this. Should I just delete that? Basically, we have this node class, and we would have to go from the node class to the hooks. Okay, that's not particularly hard. We can just add an accessor for the engine here. Then add an accessor for the hooks here. And then we are done. And now we can call this node engine hooks unrealize node, and basically the same here. Okay, and actually this file is not compiled yet, so it's not really interesting that we don't get compilation errors yet. Okay, so what does all of this code actually do? Basically, it allows us to define a graph. So basically a connection of nodes and links between them. And the links are dependencies. So basically it allows us to define basically a set of tasks. And we can define which tasks depend on others. So, I mean, if we look at the main kernel, we can probably see it used in multiple ways. For example, this in the main kernel declares that before multitasking is available, we also need to be able to create kernel threads. Okay, that's the dependency that we declare. And other parts of the kernel make use of these tasks. So for example, if we look at the PCI code, I guess, the PCI code declares different stages of the boot process, where buses become available or devices are enumerated and so on. And then it should probably also, okay, in some other file, like here, declare a task that actually does discover these buses. Yeah, and then, for example, the task that discovers the root PCI buses on x86 depends on ACPI table discovery, and after it's done, we assume that the bus 0 is available. Yeah, so here we have a task, and we can basically declare that it sits between two stages of the boot process, namely that ACPI tables are discovered, and also that, or rather on the other hand, that, well, PCI buses are available. So that's a nice declarative way to define the dependencies between parts of the boot process. And that's what we also want to employ now in the prekernel code. Okay. Okay, so we have to define something like this here, like this global init engine. So let's do that. Generic main. Maybe show the, yeah, we have, or actually using these logs that I just commented out or deleted or whatever, or replaced with generic functions, it's actually possible to draw the graph. But I don't have such an image right now. So Cookie, if you have one, you can post it in the chat, I guess, because that really illustrates well how the process looks like. Yeah, Cookie is looking for such an image, and then I can show it on stream. Okay, for now we have to override our hooks class, and we should also actually include our header. When we have the overridden class, then we can pass it now to the constructor of this global init engine. And now, now I made a bunch of mistakes in the while editing this file, because the hooks pointer is a pointer and not a reference. So yeah, we have to do this. By the way, I'm using here, I'm using a virtual class and not a template or template policy or whatever, because yeah, this is not really performance critical. I mean, if we do a few virtual calls in the during boot, like a dozen or so, then that won't really affect performance. So it's just more convenient to use a virtual class here. And actually, lots of these functions can actually be empty. The only thing that should not be empty is, I guess, this, because it should panic, and this should be no return, I guess. Not sure if it needs to panic, but yeah. It basically signals that there are dependencies that could not be met because they are circular. So yeah. Okay, let's fix these compilation errors. There's no node class here. Okay, there's only an edge class. I'm not sure if the edges actually know the engine. No, but I guess we can look at the source node to get the engine. Yeah. Okay, so this chain becomes a bit more convoluted, but it's not a big deal. And actually we should probably also not allow null pointer here. That will lead to mistakes because we're not checking for null. Okay. Now we need to define this one function here, which we just define by logging and then panicking, I guess. This should really never happen. And basically, if it does not happen, in principle, it can only happen if we make a mistake at compile time, not if something goes wrong at runtime. So yeah, it's fine to just do something stupid here and just panic. Okay, we get a bunch of warnings because they are virtual functions, but there's no virtual distractor. Actually, this class should never be distracted anyway. So yeah, there are two ways to silence that. I mean, the first is giving it a virtual distractor. The other is making the distractor not accessible. That should also silence the warning. And because we never want to destroy the class, it's fine to not make the distractor visible. Okay, we get a bunch of... Yeah, okay, that's quite stupid. We get a bunch of missing or unused parameters, which we can of course just silence. I don't want to erase the names because they might be useful if people implement this class later on. Okay, I placed final in the wrong place, right? Okay, if it doesn't go here, then I guess it goes here. Private fields not used. Okay, there are private fields that are not used. That's because, okay, I guess they are mostly descriptive. Yeah. But they are still useful. I don't want to delete the fields. So what I'm going to do is I will just make them used by adding accessors that the printing functions or the hooks can then use if they want to. Yeah, the display name, for example, is purely for debugging, but it's still useful to have it. Okay, cookie found in init graph. Example, yeah, so this is basically how the graph looks like on ARM. Yeah, so this is what we can now define at compile time, basically, and then the init graph code that we have will basically make sure that all these dependencies are met, that all these tasks execute in the right order, so that basically we start here and only execute tasks once all dependencies have been executed already. For example, there are tasks to pass the device tree, to initialize the interrupt controllers, to enumerate PCI buses, and stuff like that. Yeah. And then there are generic stages, and that's, for example, this fibers available stage, which signals to the generic part of the kernel that kernel threads are now allowed to run, or can now be created rather. There's also this tasking available stage, which means that the kernel now switches to multitasking mode, which basically amounts to enabling interrupts. But in all stages before this tasking available is reached, in all tasks here at the top, interrupts are disabled, and later on interrupts are enabled. Okay, there's a missing edge. From discover DTB nodes to enumerate buses. Where's discover DTB nodes? From here to here. Yeah, that's not ordered right now. This task is not ordered compared to that one right now because there's no edge. Also no transitive edge. Okay. All right. Nice. Then let's see. Okay, we now have this init graph defined. That's nice. We also need to define a bunch of these stages that can be reached. So let's look at the generic, or look at how the main kernel does it. For example, here, right, there were some stages defined. Yeah. And now if we look at, basically, if we look at the ARM function that I showed before, there are more or less, I think, 4 stages. The first one is when we discover that which memory ranges exist. That's the first stage, basically discovering all memory. Yeah, all memory ranges that are usable. Then, setting them up. Finding the kernel, and then building this boot info. Yeah, so I think we need, I think we need 4 stages. Okay. Yeah, let's do that. So first one is, yeah, let's call it memory discovered, I guess. So I made, yeah. Second one should be something like memory set up stage. Then kernel found, or kernel available stage. And then boot info build stage. And I guess once the boot info is built and the kernel is available, we can just boot into the kernel. So that will be when we stop. Yeah. Or actually, we probably want yeah, we probably want to have some way to express that we are ready to build the boot info. Yeah. I'm not even sure if we need the first stage actually, because the first and second is somewhat similar. So we'll see. Let's call it maybe boot info ready stage. Okay. Or boot info buildable. Okay, it's I guess some bike shedding, but yeah. Okay, that should be fine. No, it's also just the names here. And this is not this generic dot memory discovered. We also add some human readable names. Because we can later use it in debugging logs, and then we know what's already finished and what isn't. Yeah, that's the purpose of these human readable names. And now one might ask why we use some static functions. Actually, what? Yeah, okay. Why we use some static functions to define these stages. That's basically to work around global constructor order. So these things here are const init, and const init means they are initialized at compile time. So there's no runtime initialization necessary at all. And this the constructor of these classes runs entirely at compile time. But I think that's not possible for these things here, for these objects, because they insert into some linked lists and stuff like that internally, and that's not possible at compile time because they change global pointers, and yeah, const expression functions are not allowed to change global pointers. Yeah. So yeah, we need to make sure that they are initialized in the right order, and if we put them into a static function, then we know that they are initialized exactly when they are called first. Yeah. So that's yeah. So that's that works around this issue. Okay. Good. And actually, I noticed now that I said that we do not actually call global constructors. Yeah, we do not actually call global constructors, and that's of course a problem. I guess we can verify that by adding some global constructor. So but I think we aren't. So let's just log here. Hello world from global constructor. Yeah, and I think in the prekernel we are not actually using. Yeah, we are not actually calling them, which would break a lot of these init tasks. Okay, we get an undefined reference to CXA guard release, which means that some support function is not implemented. And okay, we can erase the destructor with some helper class. Okay, that does not help. Okay, because this helper function is called during global construction. Okay, and let's see how to solve that. So I think, yeah, so I think the first thing that we can do is we can say that static functions don't need to be thread safe, because by default static variables in functions are thread safe. It's guaranteed that they are only constructed once, even if you call the function in parallel. So we don't need that feature because, well, because everything is single-threaded here anyway in the prekernel. So that means you can get away with that. Oh, and that gets rid of the compilation problems. That's nice. Okay, but now we see that global constructors are indeed not called. So I think the first thing to do here is to fix global constructors. Luckily, that should be quite easy. And I guess we just steal code from the main kernel. Which is where? Here. So we steal this code. Yeah. We steal this code here. And also the code to invoke it. Yeah. When is this function actually called? Oh, okay. Not from this file. It's probably called from assembly code. Actually, that's a good idea, I guess, that we call into this run constructors from assembly code. Yeah. Okay, and then, okay, it's a problem that these init array and an init array start, or yeah, init array start, init array end functions, symbols are not actually defined in the linker scripts. So let's fix that. Let's first take a look at the linker script of the main kernel to see how we can fix that. Okay, you have this init array. It's part of the data section, I guess. Yeah, and then there are some magic linker script invocations that make sure that constructors appear in the right order, and we should just copy that instead of running our own. Okay, so we have 2 linker scripts, 1 per platform. It's of course a bit annoying that this now yeah. Oh, actually this is read-only data, I guess, right? Is it read-only data? It should be read-only data. Let's see what happens if we put it into the read-only section. Yeah, so we have 1 linker script per platform, as I said. Yeah. Okay, let's see if the sections of the resulting files are still sane, because sometimes the linker does something really stupid. Or somehow messes stuff up in unexpected ways. Linkers are somewhat fragile if you don't use the default linker script. Basically, they are only tested ever with default linker scripts and slight variations, so everything that's sufficiently different breaks. Okay, where are the binaries stored? They are stored in package build, packages, I guess. Managarm kernel, user managarm bin. Exactly, and now we have 2 binaries. Okay, this looks good because we still have a read execute segment and then a read write, and we don't want to have we certainly don't want to have a read write execute segment. If I oh wait, but something strange is happening. So the first segment is only text. And init array is actually put into the second segment. Okay, then we have init array read-only data, but that should go into the first one. Okay. Let's maybe comment this out real quick so that I can see what's going on before we make the changes to the linker script. Okay, assuming that we don't, now I have to change, of course, the right linker script. Yeah, let's go for the word one first. If I don't do that and compile, okay, I get these segments. Text read only data, data. And init array is put into data. Okay. It's put into read write. That sounds like a suboptimal choice, but I guess there's no real way we can fix that. So then let's put it here. And this now should, yeah, still result in the right segment. Yeah. It's important that, for example, we don't put read-only data into data, because then paging won't catch access to read-only data, and that's quite annoying because it will lead to security bugs, but also make debugging a lot more difficult. Good, so word works. Let's also change this. Yeah, it's a bit annoying that we need one linker script per platform, but yeah. I guess we could somehow hack around the need for that by, by changing this address here. Yeah, by changing this address using some set command or whatever. Yeah, some regular expression replacement or some preprocessor. But for now, it's fine if we just have two linker scripts. Okay, now we can call global constructors. So we should also do that. So let's change the RISC-V code to call global constructors before calling main. Jump and link is what we want to do. Now we want to run camo. Yeah. We could have one generic linker script and one per platform with just the constants, and tell the linker to use both at once. Ah, okay. Yeah, that's smart. That's I didn't think of that. But yes, you can of course chain linker scripts. Yeah, that sounds like a better solution, like a much better one. I guess I can implement that. Yeah. Okay. Yeah, now constructors are getting called. There's one global constructor. This constructor prints hello world, and that's nice. Okay. Yeah. Good. Yeah. All right. Good. So we were currently working on the init graph. So let's maybe continue with that. Yeah. Let's continue with that. So what do we still need to do? We actually need to do something interesting with the init graph. So Let's look at the ARM code maybe. Yeah. Let's look at the ARM code and see what it did. I guess the first thing it did is looking for the device tree. Yeah, it was first looking for the device tree. Maybe that's what we can do. Maybe we can just copy this part. Yeah. Maybe we can just copy this part of the device tree parsing. Yeah. We copy this part from the ARM code and see if it works. And we'll do that in an init graph task that, yeah, that runs before this memory discovered stage. Okay, actually we still have to run the init graph. Yeah, we still have to run the init graph. And maybe we also do a pre-activate function here that prints what we are doing. Oops. Good. And now, again, let's take a look at the main kernel and see how it runs the graph. Okay, it just calls .run on the engine. So that's what we are going to do here. Global init engine.run. Let's see if that builds. Display name is a protected member. Okay, I guess we screwed up our permissions. Yeah, makes sense because this should be public here. Actually, I guess. Wait, no. This is a struct, so why is stuff protected? Because I added these accesses in the wrong place. Okay, function is not marked override. That's something we can easily fix. Yeah, let's do that. Let's fix that. Let's run Camu. Okay, and I guess now what's missing is actually declaring such a task. And the tasks will just be global objects. So in the RISC-V code, yeah. Okay. I guess that should not be part of the RISC-V code. But rather we should have some system and then some DTB directory like we do in the main kernel. Yeah. Yeah. The thing is, we want to include this code from ARM and RISC-V, so let's not hardcode into the RISC-V stuff. Okay, let me grab this chunk here. Oh, but actually this device tree pointer is something that we need to pass in from the actual architecture. Yeah. So I guess what we do is we have a function that does all of this. Yeah. Okay, this is already a white point and there's no need for this interpret cast. I guess we have a function that does all of this. And now what we do is we call it from generic code. Yeah. No, we call it from architecture-specific code, sorry. Yeah. Okay. Yeah. Okay, we need to compile this file. We should also add some header for it, I guess. Yeah. Okay. And put it into the right namespace and stuff like that. And we should also include the debug header so that we have access to the logger. Okay, and then let's see if that compiles, I guess. Okay, this becomes a bit more messy now because files are stored in a different place. Yeah. They are not stored in the RISC-V architecture directory, but they are stored here. Discovery CPP. Okay, and then we are missing a bunch of includes. Okay, first of all, we're missing the third include. Then we are missing also the device tree include, which yeah, which we can get from here. Yeah, okay, it's this one. I don't know. And a bunch of other stuff. Okay, we get an unsupported architecture error here, and that's true, I guess. Oh, but I don't really want to fix that now because that's annoying. Why do we actually need libarch variables for the device tree? I mean, it's something we should fix sooner or later, but yeah, why is that needed? It's needed for endian conversion. Yeah. Okay, it's needed for endian conversion. Okay. Well, the issue is there's the sub-project that we have in a different repository, which, yeah, has a bunch of functions to access memory and I/O ports or whatever, for example, memory mapped I/O or port mapped I/O, in a generic way. Yeah, and using some nice interface. The issue is, of course, it it needs to have some architecture-specific code, and for RISC-V, this code is just missing right now. The thing is, I don't really want to implement that now, but I guess I have to. Yeah. I guess I have to. Okay, but yeah. But I first want to commit the init graph stuff. Yeah. It would be a bit annoying to now do this, and then we have a bunch of open issues at the same time. So let's maybe just lock here the pointer and get rid of all the other code. Yeah, so that we can actually make progress with the init graph, and then in a different session adjust the device tree code. Okay. So I want to call this now from architecture-specific code. Yeah. Which means I want to call it from some new file, I guess. From some file that we put here. Okay, so let's add this this DTB file here. Then fix the header inclusion, which means including just including that, I guess. Yeah. That should fix it. Oh, I might not have created the header in the first place, did I? System TSG binary. Yeah, I didn't. Discovery HVP. Yeah, we do a pragma once, open the namespace, declare the function. This one. Here. And then we should be done, right? Yeah. Okay, and now I want to add here such an Now I want to add here such an init graph task that calls this. Okay, let's do that. I guess I'll take a look again at Thor to see how the tasks look like. Yeah. They look like what? Like this. Okay, they are static. variables. Yeah, discover memory. Okay. We need to pass the init engine. We need to give it a name. RISC-V dot discover memory, I guess. And then we can pass some dependencies, which we don't need right now. And then we just have a lambda. Yeah. That does something. And now we need to pass in the pointer. Yeah, we need to pass in the pointer. And I guess we just store the pointer in some global variable that the boot code sets. Yeah. Yeah. I guess we do it like that. Okay, now there's also the issue that we need that the init graph include is missing, but we also need access to this global init engine, which means we need to put it into some header. And after we've done that, everything should work. Okay. Do we have a header file? We don't have a header file, an appropriate one, I guess. So, yeah, let's see what header files we have. Do we have a main HPP here? No, we don't have a main HPP. So let's just create one. And now we just declare the init graph engine global init engine. Yeah. And then we are done. Okay. Okay, this needs to be in the namespace. Yeah, let's put everything into the same namespace. Like this. And then I guess we also need to do that here because we did not do it so far. Which also means that we can drop some qualifiers here, which is nice. Okay, we get an undefined reference. Why do we get an undefined reference? Because extern C implies extern, I guess. That's a bit annoying. Okay, I guess we can just drop the extern C for normal symbols because it, yeah, there's no name mangling for functions. But we still need to set that, of course. Yeah. So yeah, let's set that from our entry point. And now I have to take a look again at the ToyOS to see where the device 3 pointer is passed. Okay, it's the second argument. The second argument to the entry point. Right, So yeah. I guess we can just load the address of the symbol here of the TTB pointer to some temporary register. Yeah, I should probably do that before calling global constructors. So, for example, here. So we load into some temporary register. We load this address. Then we store. What's the syntax to store again? Okay, it's store. Then the register and then the offsetted address. So argument, what did we say? Argument 1, and we want to store it to T0. That should be the syntax, right? Yeah. We get an undefined reference here. Why do we get an undefined reference? Because it's in the namespace, so name wrangling is actually active. Okay. So let's move it out of the namespace. Okay. Yeah. Okay, now that works. Now it's running. When it's running the global constructors, it registers this task, and then later on it runs it. Yeah, and this is apparently the device tree binary pointer, which looks fine. It doesn't look like a broken pointer, so it looks like something reasonable. Oh yeah, and the OpenSBI also logs this value here, which means that things are going correctly. Good. I think I will stop the stream at this point. And then next time I will basically complete these init tasks, or maybe first get this to run on real hardware. Yeah. Yeah, but then basically what we will do is we will add appropriate init tasks to do all the stuff that the ARM main function does right now. Yeah, and then hopefully we will be able to load the kernel, and then yeah, we'll start working on the kernel, I guess. But that will take still a bit of time. Okay, so thanks for watching, and